Okay, welcome to a new unit. This is chapter 5. We're going to be modeling with graphs. So last unit we spent modeling with algebra and variables and expressions and those kinds of things. And now we're going to be taking those expressions, those equations, and graphing them. So we'll often have two variables. That's two things that can be represented by a letter. And they'll relate to each other some way, some shape, some form. So for instance, the amount you get paid and the number of hours you work. There's two variables, right? The hours you work and the amount you get paid, and they relate to each other. And you could graph that relation if you knew the rate that you were getting paid. Okay? So that's kind of what we're getting into right now. Just basic introduction, rational numbers. This should be review. But at the top of there, you can, right in the middle, draw a number line. And that number line is going to go 0, 1, 2, -1, -2. Now what we've drawn so far are integers, but what we're going to do is split this graph up 1, 2, 3, 4, 5, 6, 7 into, so a little line in the middle there, a little line in the middle, a little line in the middle, a little line in the middle, and do it again. Again,
are we doing fractions?
Rational numbers is any number that can be expressed as a fraction using whole numbers. So cutting all those in half again.
I don't have enough room for that.
It doesn't really matter if yours is exactly like mine. We're just going to identify some rational numbers. The first one that we're going to identify is way down here at -1.5. Okay? So, here we have -1.5. Now, can you think of another way to express that same value?
Yeah. 4, no. 3.
We'll take the -1.5. Jacob?
-3/2.
-3/2.
How do you say that? Because that sounds weird if you say
-3/2 or -3/2. Okay? Now if we look at this thing, there's actually two other ways that we can express this without changing the value at all. Right now, the negative sign is right out in front. Where else could I put that negative sign?
Both.
I could put it up top in the numerator. Or I could put it down below in the denominator. Now, could I do this? Could I put it in the numerator and the denominator?
No, because that'd be positive.
Now it's a positive number, so this is incorrect. Okay? There's several ways of expressing the same value. Okay? They are equivalent rational numbers. Let's go up over here to this one right here. It's 1 3/4 as a mixed number. Can you think of other ways to represent 1 3/4?
1.75.
As a decimal, it's 1.75. What about as a improper fraction? 7/4. And that's the only way, really. You could put a negative sign in both the numerator and the denominator, but that's a bit silly.
14/8.
Okay. Right, we could also, you're right, we could keep going here. We could say, oh, this is also 14/8. Good call. Okay? So often, rational numbers can be simplified. Who knows another way to say simplified?
Reduced.
Nice, reduced, or expressed in lowest terms. So 3 ways to say it. Here's just a little example of that. Let's say you were given -9/16. 6. What would we do to reduce that into lowest terms?
Divide by 1.
We could divide the numerator
By the denominator.
and the denominator by 3, by their greatest common factor, which would give us negative 3 over 2. Now notice
1 and 1/2.
we did the same thing
To both sides.
to the numerator
And the denominator.
and denominator. Go ahead and write that. And that's rational numbers. Should be already pretty good at that. There are practice problems for 5.0, but we're going to finish off our lesson first. So there's your notes on rational numbers. Okay, ratio and proportion.
That's
Again, this is something that we have done already this year, but it is hard to sometimes remember to apply everything that we've learned. So we're doing a quick review of ratio and proportion. It says the body weight, and you can picture all this, of a 50 kilogram woman contains about 25 kilograms of water. So you've got a ratio there. Second part, the body of an 80 kilogram man contains about 48 kilograms of water. So you have another ratio there. And we need to find the mass of water in the bodies of a 60 kilogram woman and a 60 kilogram man. So the first thing we're going to do is just fill in that chart with some of the information. The first column is going to be called person. And then from the information we're given, we're going to develop a ratio of water to mass. So the ratio is water to mass. Then we're going to reduce that ratio to simplest form. Then we're going to express as a fraction. Now once we've expressed it as a fraction, we can then use it really easily as a factor in finding out the problem that we want to find out, which is the mass of water in a 60 kilogram man and a 60 kilogram woman. So first thing that we were given was that we're dealing with a 50 kilogram woman. And what is the ratio of water to mass in a 50 kilogram woman?
25.
Okay, so water comes first, 25, and here's how we would write that, 25 to 50. Can we reduce that into simplest form?
1 to
Everyone's good with that?
2. Mm-hmm.
And can we express that as a fraction?
1 over 2.
1 over 2. So I'm going to actually just show the original ratio and then show that that's reduced to 1 over 2. Now what about our 80 kilogram man? Go ahead and fill in the chart for... This is the information that we're given. 60 is what we want to find later on. So go ahead and fill in the chart based on the information in the problem.
Where did you get 48 from?
Question. That's some.
Sure.
And when you've done it on your own, you can double check up here to see how you did.
Is 48 like exactly 3/5, or is that just like a...
Exactly 3/5. You divide both of these numbers by 16. So if you're not sure how to do that, I would start just cut them each in half. So if you cut them each in half, you get 24 to 40, and you realize, oh, they're still both even numbers. You can cut it in half again. 12 to 20, oh, they're both still even numbers. So you can cut it in half again. 6 to 10, oh, they're both still even numbers. You can cut it in half again. Oh, now they're both prime numbers. Can't reduce any further. Okay, so there's a little tip for that. All right, so now we're going to try to answer our question, which is find the mass of water in the bodies of a 60 kilogram woman and a 60 kilogram man. So for the woman, we know that water relates to her overall weight by a ratio of, or a fraction of, 1/2. So all we have to do to find the amount of water in her body is take her weight and multiply it by 1/2. 30 kilograms of water.
Where did we get the 30 from?
The birthday is in the calculator.
16 times 0.
For the man, we do the same thing. We know the man is 60 pounds, and we know that the water relates to his weight by a ratio of 3/5. So all we have to do is multiply this out. Top times top is 180 over 5, which gives us a final answer of 36 kilograms of water. Okay? So all we did was we found a ratio that relates water to mass. We converted it to a fraction. And now we could do this for any man, any woman in the whole world. Tell us your weight. We can tell you how much water approximately is in your body. Okay? Does that make sense? For a woman, you cut it in half. For a man, it's 3/5. I don't know how true that is, but that's what our example is. For the last thing in 5.0, we have a review of percents. So we have our friend Fred. Over the track and field season, the height Fred cleared in the high jump increased from 1 meter 81 centimeters, so 1.81 meters, to 1.96 meters. So we have an increase in his high jump. That's pretty high. He was hoping to have a 20% increase in height. Did he? What do you think?
No.
Why not?
Because I'm different. Whatever the people say, then I say
1.81 is too close to 1.96 to be 20%?
I believe
You'd
in
have
that
to have
too.
like 40, almost 40.
You have to believe.
Yeah, if you're hovering around the 2 meter mark, then 20% is approximately 40 centimeters. Okay?
It was
We're
only like 9%.
So let's find out what the percent actually was. And the first thing we need to determine is the, taking notes,
That sucks.
Meter 96.
height increase. So how do we determine the height increase? The height increase is the difference between the height he can jump now and the height he could jump at the beginning of the year. So whenever you hear the word difference, you're thinking subtract. So we've got 196 minus 1.81, which equals 0.15. Should have your calculators out.
15%.
Should have your calculators out. Oh, careful, because this difference, it's not out of 100. It's based on the amount that he could jump before. So we need to be careful with that. So far we just have his height increase. Now, to calculate the percent increase, we need to follow this model. It's going to be the height increase over the original height times 100%. Okay, so if we left this part out, the times 100%, we would get this part expressed as a decimal, and that would be fine. We would understand that probably, because it's the same way you punch to get the percent of your test in your calculator. You'd understand that. If you multiply that by 100, you get what the actual percent is, because percent just means out of 100, right? Per 100. So we have these amounts. We have the height increase. What's that?
15.
Yeah.
I.
0.15?
Same thing.
Nope. And we have the original height,
Of 1.81
1.81. Okay?
equals.
You multiply that by 100. So you can do that in 2 steps in your calculator. Just do 0.15 divided by 1.81, hit enter, and then hit times 100.
It's like 8, 9.
44.
8.28. somewhere
Around
like
to 1 decimal place is typical.
0.27.
You go, bro. Do you divide 0.15 divided by 1.81?
That's what it says.
Yes, sir.
All right, Fred
He's not even.
increased
Yo, I got a name of you, Fred. My dude's so tall.
his jump
Fred.
by
But he's old.
8.3%.
Close to 20.
Not even close. Well, how much would he have to have done? How high would he have to jump in order to increase it by 20%? We're going to do that one as well. For a 20% increase,
I believe in Fred.
multiply original height by 20%. What does that look like in my calculator if I'm doing that by 20%? 0.2, yeah. Or 0.2.
Can't you do like 1.2, then you'll get like that original one? If it's
Yeah.
you don't even have to add it on.
Yep. And add to original height. So we're going to do 0.2, that's 20%, times his original height. And what's that going to give us?
36.
Nope.
That's not 36.
0.362.
That's what I said.
Good. And now we're going to add that amount to the original jump height.
We just did that.
Nope, we didn't. So go ahead and add 1.81 to that.
2.172.
So if Fred wants to jump 20% higher by the end of the season, he needs to have a jump of 2 meters and 17 centimeters.
Sam can
Okay?
do that.
It's pretty high. Now, one of you called out, hey, can't we just multiply by 1.2? Yeah. If you wanted to find out, you could just take the original amount,
No. Yeah.
multiply it by 1.2, because this will represent 1 times his original jump, which is just his original jump, plus 20% of his original jump. And that will right away get you 2.172. Okay, so go ahead and try that in your calculator as well.
It gets the same answer.
Where do you get 1.2 from?
We learned this in this.
So this is 100% of his original jump plus 20% of his original jump, which is exactly what we did on the left here. Your practice problems for 5.0 are on the next page.